here, right? This term over here will always be less than what? 1. Okay. So if I'm going to sketch a graph, right? Sorry, I just combined the lecture and the example together, but I think I want you all to know. So if I were to plot now, this is frequency. Okay, if this is frequency, and over here, this is amplitude of deflection. What you tend to see is you tend to see two peaks. Okay, what do I mean by that? Okay, so this is the first peak. And then it's normal to have the second peak to be higher. Okay. So the first peak over here is known as your omega d. And the second peak over here is known as your omega n. Right? Yes. This one? Yeah, so that is just omega, but omega is also equal to omega d. Equal to omega d. They usually omit them. Some textbooks have it, some don't. So now, then later in the fourth vibration, we have omega naught also, different things. Right? Okay. Now, can someone explain to me why the amplitude of omega d is lower than omega n? We know the frequency. Yes. Energy being absorbed or energy being dissipated. Yeah. Bang on. Okay. Because the damper dissipates the what? Energy. The kinetic energy. That's why the amplitude of vibration is lower. Okay. Right. So coming back to here. Okay. So we have come up with an expression where omega is equal to omega square root of 1 minus zeta squared. Okay. So the next thing we do is we are going to calculate our zeta. So zeta is equal to c squared over 4mk. So square root of c squared, our c squared is 50 squared, divide by 4 mass and 1250. Okay, so our k is 1250. So from here, we get 50 squared divided by 4 divided by 9.072 divided by 1250. Square root of the whole thing is 0.235. Okay, I'll do it again. Divide by 4 by 9.072 divided by 1250. Square root of the whole thing, 0.235. Okay. So any values that are important, I will highlight. So this is an important value to me. Omega n is an important value to me. So from here, we can compute what is our omega, which is also equal to our omega d. So this is equal to omega n square root of 1 minus zeta squared. Okay. A student asked me yesterday, why should we calculate zeta? It's for this reason. Can you see if we don't calculate zeta, how complex your formula can be? Yes or no? Right? By allocating a certain constant, your formula will be easy. Will your calculation will be easier. So this will be equal. So omega n 11.738 square root of 1 minus zeta squared. Okay, so 1 minus by 0.235 squared, square root the whole thing times by 11.738. So it's 11.409 radians per second. Again, another value that is of importance to us. So now, the next thing that we have to remember is we have to recall the graph on performance measure. Okay, and it's not that difficult to remember. You can sketch this out. Are you okay? Can I move on? You're okay? Any questions so far? Yes. It's just a number. We call it damping ratio. Anyone else having questions? Now, if you put up your hand for too long, just say excuse me, okay? Don't wait to, you know what I mean. So from here, I forget what we're going to do now. I remember now. So you have to recall. So you have to just sketch this. Okay. And you just need to label this XSS, omega t. You have this. Right? And the first one over here, this is your first what? Overshoot. And we know that this is equal to pi, right? So because it's the first overshoot, you will automatically know that this is your TP. Okay, your first time to the first peak. And then immediately halfway, this is pi over 2, right? This is your TR, right? And then if you have your certain range, again, this is just a sketch. This over here is your 0.2% XSS, or 2%, not 0.2. I beg your pardon, 2%. So over here, this is your second overshoot. Okay, and we know that this value over here is equal to 3 pi, right? Because the distance from here to here, this is your 2 pi. And then up to a certain point, right? From here to here, this is your TS. Okay, you just need to remember this diagram. And then the next thing is your boundary condition. Omega t is equal to 0, x is equal to 0. Okay, that is your boundary condition, right? So what we are going to calculate based on the question is we are going to calculate our rise time. So our rise time is omega TR, which is equal to pi over 2. TR is equal to pi over 2 omega. And pi 2 omega is your damped natural frequency, which is equal to 11.409. You put in 11.409, and then you calculate. It's equal to 0.138 seconds. 1 mark go into your pocket. I'm serious. Get straightforward, right? If this question is worth 15 marks, 1 mark go into your pocket. It's a freebie. Yes or no? The only thing you have to remember is what? That diagram that we've just drawn. Okay. The next thing, peak time. Again, look at the diagram. Omega TP is equal to what? Pi. So TP is equal to pi over omega. So pi divided by 11.409. So it's basically twice the time. Is equal to 0.275 seconds. Next thing, we are going to find the percentage of overshoot. From the formula sheet, you know that the system response is x as a function of time. This is equal to E minus zeta omega nt bracket C1 cos omega t plus by C2 sine omega t. And then you have to plus XSS, overshoot. When it settle down to 0, XSS is equal to 0. But if you look at this graph, XSS has a certain magnitude. Yes, just put in x-axis. So from here, don't worry about C2, okay? Because C2 is what? Sine omega t. Somehow, if you look at the solution, right, it will always turn to become equal to what? 0, okay? So if we look at the percentage of overshoot, okay, we know that the time for first overshoot, we focus on the first overshoot because the first overshoot, the amplitude is the what? Highest, yes or no? We focus on the first overshoot because its amplitude is the highest. So you already know that we have what? Omega t is equal to what? Pi. So therefore, omega t is equal to what? Pi. Yes or no? Right? So from here, we also know that t is equal to pi over omega. Why? Because the equation over here is in terms of what? Time. Okay? That's why you want this expression where time is equal to pi over omega, where you will see your first overshoot. We want to know the first overshoot because the percentage of overshoot will be at its what? Highest. Later on, when you go to the second overshoot, it will what? It will die down. Are we clear? Okay. Don't let the math frighten you. I'll tell you this though. By the time you finish second year, your math will be better than mine. Are we clear? Okay, so don't be afraid of the math. I can survive so long with the math I have, you will be doing better. Right. So from here, what we're going to do is we are going to incorporate, or we're going to use boundary condition to determine C1. So that's where we use when omega t is equal to 0, x is also equal to what? 0, right? So where is this? This is over here. Can you see this diagram over here? Okay. Good. Is my handwriting big enough, or you're okay? You're okay? Good. So we know now that this is equal to 0, E minus zeta omega n multiplied by 0, right? Or yeah, 0. So this is C1 cos of 0 plus by C2 sin